Hello everyone. I'm just going to give it a couple of minutes for everyone to join the room, and then we'll begin. Okay. Good afternoon, everyone, and welcome to the University of San Francisco's MSDS seminar series in data science. My name is Sean Butcher, and I'm the Partnership Director for the Data Institute. This seminar series is brought to you by the University of San Francisco's Masters in Data Science program and is sponsored by USF's Data Institute. Each year, we partner with companies and organizations around the San Francisco Bay Area and beyond to provide 9-month internships for our students. During their degree, our master's students spend 15 hours a week working with companies to tackle their data science and analytics problems. If you or your organization is interested in supporting the Data Institute or working with our students, please contact us by email at datainstitute@usfca.edu. Alternatively, you can visit us on the web at www.usfca.edu/data-institute. I want to also give a big welcome to our newly admitted Masters in Data Science students. On behalf of the Data Institute, I want to thank you for attending, and I look forward to working with you in the future. Today, I'm pleased to welcome John Mount. John is co-founder and principal consultant at WinVector LLC, a San Francisco data science consultancy and training company. He's the author of several R and Python packages, and he is co-author of Practical Data Science with R, published by Manning Publications. His talk today is on how and why to use probability models to outperform decision rules. We'll be leaving some time at the end of the talk to answer your questions, and I'll try to answer some of your questions during the talk. If you do have any questions, please enter them in using the Q&A button at the bottom of the screen. Don't enter them using the chat function. We won't answer your questions there. So please use the Q&A function. Welcome, John.
Well, thank you very much, Sean, Leslie, and Kirsten for hosting me. And again, I do want to apologize that Nina Zumel couldn't make it today, and I'm going to substitute for her. It was going to be a 2-person talk, and I'll do my part first. She's not here to defend herself. And the topic I want to talk about is basically, I need to take over the share.
Okay.
Sorry. The topic I'd like to talk about today is there. Am I sharing?
Yes.
Yeah. Okay. So sorry. The topic I would like to talk about today is why to use probability models to build your models when you're doing classification. And the idea I have is that essentially, let's just define our terms. So sorry, I had that open ahead of time. I do apologize. There it is. Sorry, I opened everything ahead of time to save problems and, of course, cause problems. I think that's called Galileo's principle. Anyway, the topic I want to talk about is, I think should be available to everybody, is we have a type of machine learning problem in our business called classification, which is given explanatory variables, which are values you know, and a dependent outcome, which is what you are to predict what level our symbolic value that dependent outcome will have. Like, is it yes or no? Will the person buy the item? Will the person click on the ad? Does the person have the disease? So predicting a categorical outcome instead of a number is called classification. Now, there's a often taught mistake in data science that basically, let me stop the share for a second, that we teach that to solve a classification problem, one should build a classifier. And I'm going to say basically that's very common bad advice. that really what one should do is build a probability model, that the actual classification is a defect of the training data, that if we are saying whether somebody has the disease or not, we're actually more interested in the probability of them having the disease, whether a particular individual has it as the data scientist. Obviously, the individual cares only whether they have it or not, but as a epidemiologist or a data scientist, we actually care more about probabilities. Now, this bit of advice is very easy to execute. It is, you don't need a new set of modeling systems. You just need to say, if you're using Python scikit-learn, call predict prob A instead of predict. That's the entirety of the advice. However, and what the content of these two talks is, what do you do with that probability? And why are there so many weird things like data rebalancing to deal with rare classes? And what we're going to say is these are a lot of tools to get around the mistake of having used a classification outcome instead of a probability in your modeling. And so that's the topic I'm going to do today. So let's turn the share back on. So it'd be two 20-minute-ish pits and adding up to about 45 minutes and then some time for questions. So I presume I'm showing my worksheet KDD 2009 resample. This worksheet and all the slides from the talk are available at a URL that will be shared in the chat. It's essentially WinVector, GitHub, examples, scoring models. But let's go ahead and work through the thing. So this problem is a classification problem from 2009 that was shared at the KDD conference as a contest. And the contest was to build the best model to predict this categorical outcome. The categorical outcome was called churn, which is the technical name for the cancellation of a financial account. So this was a credit system, and they wanted to know which accounts are most at risk for canceling, because those are the ones that maybe you can intervene, like maybe reach out, offer them a discount or something. So knowing which accounts are most likely to churn or cancel is a very big deal. And as I said, all this code to be shared in a link to be shared in the group. So what we're doing, again, we're working here in Python scikit-learn. I'm importing all my packages. I always do that as the very first step in any Jupyter Lab or Jupyter worksheet, or IPython worksheet. That way, if the system is not correctly configured, I detect that very cheaply and early in my data science process. Now I'm bringing in the data. All this code is irrelevant. It's just to set context to get us to the point. And now I'm doing some data treatment. Now, a dirty little secret of scikit-learn style packages. I think I'm actually going to use XGBoost, which is not technically in scikit-learn, but a dirty little secret of a lot of these machine learning packages is they only accept numeric columns as input. If the package is good and you give it a string valued column, it will throw. And if the package is bad, it might actually just recast it. So you have to convert your data from the wild, which may have columns that have string values, into all numeric. Now, the canonical way to do that is, of course, scikit-learn, pre-processing, one-hot encoder. However, the way I like to do it, and this is sort of a little advertisement here, is I like to use our WinVector package vtreat. When I'm working in R, I use vtreat. When I'm working in Python, I use vtreat. vtreat does all the work of a one-hot encoding and a little bit more, and it explicitly manages column names. I believe as a data scientist in working in pandas, so I believe there should be meaningful column names. The original problem did not have meaningful column names. This is an example of the data as it comes in. The column names were meaningless. Many of the values were missing, which is often annotated as nan, none, or null. Some of the columns were numeric, and some of the columns had string values, and it looks like these are encrypted so that the data, since it was going from their credit processing into a contest, they were trying to clean it up a little. I think we've now come to the point in data science where we say encrypting values is not a safe way to, quote, clean up data and remove PII, but this is back in 2009 where they didn't think so much about that. So this is how they tried to make the data safe to share. So again, we need to reprocess this data. I like to do it in one step in vtreat. I have some links and teachings on that and some videos. But basically, it takes this original data frame and it builds a new data frame. and it says var 84 is bad, this is an indicator or a dummy. It's ones and zeros only. And it's 1 when variable 84, which was the name of that column, had a missing value. And Nina and I, Dr. Zumel and I have found that in data science, often retaining which columns are missing is very informative. So the normal way of dealing with missing values, or a common way, is to impute them, which is the build a machine learning model to replace this missing value with a plausible value given the values in other columns. So that's called imputation. The simplest imputation would be take the mean or the median of all the non-missing values in the same column. That's a very common imputation called simple imputer in scikit-learn. So vtreat does very trivial imputation like that, but it also lands an additional column saying whether the imputation happened or not. And it turns out that column is often very informative. So vtreat prepares the data. It does a slightly technical thing we call a cross frame, that when replacing the data frame with a data frame built by looking at all the data at once, you can introduce a certain type of bias called nested model bias, which will cause your model to perform better on training than it will in the wild. So vtreat gets around that using cross methods or something very similar to cross validation, not the topic of this talk. Now, what I'm going to do is I'm going to fit the model. And as I said, I'm using XGBoost. I like to use XGBoost is a basically gradient boosted trees. It's a very popular package that's available in R and in Python, has a lot of interfaces, often wins contests. I'm going to use it with basically its default hyperparameters. I'm not going to really do any hyperparameter search. Obviously, one can improve the quality of models by doing that, but it's not the topic here. And I am going to cross-validate for the number of trees in the gradient boosted tree model, because I consider that hyperparameter one of your best controls for overfitting or excess generalization error, i.e. the tragedy of models that work well in training then don't work when you put them into production. And so I'm basically, this is just the technical details of cross-validating for how many trees or generations we want, and then returning a model with those parameters. So this you could all get from reading the XGBoost manual. I'm not cross-validating for tree depth. I think I just set that to a value I liked. Often that's 3 for me. So I fit the model. And again, the explanatory variables are what we figure would be known, and the dependent variables what we're trying to predict, which in this case is the categorical, did they churn or not? And this data set has tens of thousands of rows, about, I think, 600 columns, quite a lot of columns, mostly missing values. It has categorical variables, and it has high degree categorical variables. That is, categorical variables that take on very many levels, like zip code. I don't think zip code's in this model, but zip code's an example. United States zip code is 5 digits, so that can easily take on 70 to 100,000 values, which produce both data processing problems. You cannot just one-hot encode them, and statistical efficiency problems. Even if you could one-hot encode that to many, many columns, you may not have enough data to do a proper inference unless you do something clever. And so basically, vtreat handles all that accounting for you. It's a package we're very proud of. Now, this is the model. And what I'm showing here is the, I called predict prob A, which is the topic of this 20-minute sub-talk. And I didn't call predict. Now, predict would say for each person whether they believe they churned or not. Predict prob A gives the model's estimate of the expected probability or expected value of churning. So it gives a number between 0 and 1. Now, because I have this numeric prediction, I can build up an ROC plot, a receiver operating characteristic plot. Now, that plot is a little abstract and doesn't represent business needs, which is the topic of the second talk, Nina's portion I will give here, but it represents every possible trade-off of sensitivity to specificity. Though obviously ROC plots, the x-axis is 1 minus specificity, not specificity. Now I'm a mathematician, so every time I say obvious, I mean very hard to remember. So that's why this plot puts down the labels, that the x-axis is false positive rate, which is equal to 1 minus specificity, and the y-axis is true positive rate, which is sensitivity. So if this classifier, if this score, which is a probability, were used as a classifier at different thresholds, We can say if it's above 0.2, I'm worried about the person. If it's above 0.4, I'm worried about the person. That selection of policy is called a threshold. This is the summary of this probability score at every possible threshold. How does it behave as a classifier? And in my opinion, classifiers are very well characterized by two numbers, often sensitivity or specificity, or if you're in a different family, maybe precision and recall. Not all synonyms, but related ideas. So this says, for this probability score, what is every possible trade-off as we build different classifiers? So sensitivity is what fraction of the people that are canceling their accounts did you trigger? And specificity is what fraction of people that are not canceling their accounts you left alone. So we want a classifier in this upper left that simultaneously achieves sensitivity 1, finds all the at-risk accounts, and specificity 1 leaves all the at-risk counts alone. So this is the perfect classifier up here, not achievable. We can only achieve this gold bar. We can be perfectly specific by saying nobody ever cancels, and we can be perfectly sensitive by saying everybody cancels. But obviously those are very low quality classifiers. So the contest used at the time area under the curve of the ROC plot as the contest metric. So they didn't have a business goal, and they just used as an immediate goal, what's the area under the curve? And the winners, I believe, achieved 0.79 or so. It's written down in the references. This is the behavior on training. It got an area under the curve of 0.77. And then on test, it got an area under the curve of 0.75. So it didn't win the contest, but with no hyperparameter tuning and automated variable treatment or preparation, we're in the winner's circle. So basically, we've automated all data prep that's automatable, leaving time for more important domain-specific data prep. For instance, this might take a zip code and encode it in some way, but as a data scientist, I would say, if I have a zip code in my data set and it's ethical to use, which is a really big question on zip codes, if I really should join in a census table, that the zip code's not an interesting variable by itself. I should join in things like demographics of that region. So basically, often these high categoricals, you can do something domain thing. Now, this is getting into our next topic, that the ROC curve, I think, is a very good tool, but is somewhat limited in its legibility because it is too compressed. It shows the trade-off of the classifier for every single threshold, but the thresholds are exactly what's not shown. So it says there's some place where you achieve a specificity of 0.8 and simultaneously a sensitivity of 0.5. I'm just reading off the coordinates of this graph. I have to subtract 1 because this is 1 minus specificity. So there's a classifier that achieves a specificity of 0.8 while a sensitivity of 0.5, but we don't know what classifier does that. What is the number we should compare it to? So Nina has supplied in both R and Python a graph that we call the threshold plot. And it's basically the ROC plot slowed down and unwound. So it says you can achieve a specificity of 0.8. I'm reading this off the y-axis. And that would be a sensitivity of about 0.5. They're in the same x position. And that happens when you use a classifier threshold of 0.1. The model realizes that by saying, I'm worried about everybody with a score above 0.1. And you can answer questions. What if I use 0.5 as my score? Well, it says you have a specificity nearly 1. You leave all the people that aren't canceling alone. And you have a sensitivity very near 0. You're not detecting a lot of the churning accounts. Now, the threshold of 0.5 is interesting because that is the hard-coded default of most classification software, which is why not to call predict, but instead call predict prob A. If we had called predict, so I do know how to call predict, I do it right here, what we would get is what's called a confusion matrix, which I think is a delightful name. And it says the column is what the classifier said, and the row is what the truth value is. So the classifier only said that 15 accounts were at risk of canceling, 6 plus 9. And it was right a little over half the time. 9 out of 15 there were canceling. However, there were really 369 accounts canceling in the test set, and it only picked up 9 of them. So basically, this classifier is achieving its high specificity, leaving the innocent alone by basically never saying anyone cancels, which is not a high utility classifier. Now, how did that happen? Well, this is a plot which I think explains it. This is called the double density plot. So the orange is the distribution of classifier scores for people that are known to, for people that are known to cancel their accounts. And the blue is the distribution of classifier scores for people that are known not to cancel their accounts. Now, the point is these two distributions are somewhat, sorry, I said that wrong. Positive's the bad one, as they say in The Simpsons. The blue curve is the distribution of classifier scores for people that are going to cancel. And the orange curve is the distribution of scores for people that didn't cancel. And as you can see, the blue curve, the mean is to the right, and that there's cuts here that would give us interesting things. However, the default of 0.5 is so far out in the tail, there's essentially no data there. That's what this table said. That basically there wasn't enough features for the model to become confident on exactly who's canceling. However, it still thought that this person might have a way higher chance of canceling than this person, but it wasn't willing to say numbers as high as 0.5. And this is very typical for unbalanced data problems, which is why people tend to rebalance the data. In this data set, 7% of the people cancel their account. So a lot of people say, oh, I don't get good performance at this default threshold of 0.5. So what I will do is I will rebalance my data. One is by downsampling, throwing away negative examples because I have more of them, so I can afford to throw some away. That builds me a new training set where half the data is positive, half the data is negative. Now that's statistically inefficient. You threw away data. Or upsampling, where you reproduce the positive rows that are rare until they're half the data set. And that breaks your row independence assumptions. So that's also dangerous. So now all of your significance calculations are wrong. So, however, that is the canonical advice, that if you're getting a bad classifier because your prevalence or chance of the outcome happening is not near a half, well, then you should resample your data to get it near a half, and then everything will work better. I do not like that advice because I think there are easier ways that are actually more effective to get around it. And that easier way, we're actually right up almost to our conclusion, is build a probability model instead of a hard classification rule, and pick a threshold other than 0.5 and use this threshold plot to pick the threshold based on business needs. What sort of sensitivity and specificity does your application support? Like if it's an initial screening test for COVID, it's got to have high sensitivity or recall. Or if it's a final test to determine what rate of the population has COVID, it's got to have high accuracy. Or if it's the final test before doing an expensive and dangerous surgery, it's got to have high specificity, leaving the innocent alone. So this hard-coded threshold of 0.5 is what's the problem. The industry tends to build complexity. We're all software engineers when we're data scientists, and us software engineers love complexity. So building an entire framework into scikit-learn pre-processing or to rebalance the data is considered an attractive solution. Now, this is where the rest of the worksheet is. I took several rebalancing systems from a package called imbalanced learning. So they have a paper, they claim they're solving the problem. I am doing the sin of calling somebody else's baby ugly. This has helped a lot of people, and it's an important package. And so I'm taking a bunch of their resamplers. This is their random oversampler. This is their random oversampler with a different density strategy. Undersampler, those are the two I mentioned. This is one called SMOTE. This is one called Addison, and this is one called SMOTE ENN, nearest neighbor. So these are name brand methods. So they do something complicated. And what they do is they resample the data. So I'm going to build models using their resampling systems and see what happens. And now we're at the punchline. They build a hard classifier, a decision rule. So each of these resampling plans, I retrained and rebuilt the entire data, and they have as a classifier a certain sensitivity and specificity. I've plotted each of them as a red dot on this graph. And really, and this is a study I stole from Nina. She did this some years ago in Does Balancing Classes Improve Classifier Performance? She worked out empirically, a lot of these resampling plans, all they're doing is sweeping along the ROC curve, that they're misinforming the subsystem as what's important, sensitivity, specificity, causing it to build a model that behaves differently. But really, they're not building a model that's fundamentally better than the probability model we built at the start. They're just sampling different parts of the ROC curve, which we can do with a single model just by changing the threshold. So what to look out for, the negative connotation here, is none of these dots are outside the curve. If they were outside the curve, that means they achieved a sensitivity specificity combination our model cannot. And they're all at or inside the curve. They've achieved nothing. And to get different ones, you have to retrain. And I don't know how to get them up into this region. Like they don't have a dial that says what sensitivity, what specificity do you want? They say we're just fixing things. Now, I also plotted their ROC curves. My curve is the gray one, theirs is the gold one. So if you did call predict prob A on their models, you're essentially getting about the same as the original model here. They came out a little here. That's good. Being out is the winner, gray is us, but they're inside here. They're building an inferior model. So this is just trying their different name brand methods and saying, well, how did you work as a probability model? And that's the entire topic of this talk. And just to summarize it back, that basically I feel, and I could be wrong, if you don't agree with this premise, I make no sense from this point on. I feel it is overtaught to use classification rules to solve classification problems. And I've actually seen people make fun of people on the net saying, if your model computes a probability, it's not a classifier. And I would say, well, it's not a decision rule till you say, what threshold am I worried about? So one is, I don't like building classifiers to solve classification problems. I consider classification problems censored data. I would like to know what the probability of the outcomes are, not just whether it happened to a given individual or not. So build probability models and don't bother to resample data until you know you have to. That many machine learning softwares actually do work quite well with imbalanced prevalences, despite claims to the contrary. And it's just using the hard-coded threshold 1/2 is what makes it appear. For instance, logistic regression, it has an intercepted DC term. The math says it doesn't care about imbalanced classes. It literally cannot be hurt by it. It will change the answer, but it has a degree of freedom that literally talks about class balance. So you rebalancing prior to going to logistic regression mathematically cannot do anything major. That's just not possible. And so anyway, that's the topic of the first. I apologize, I cannot see the chat or Q&A. Were there any questions that coming through while I was doing that? I do apologize.
Yeah, there are a couple of questions just come in. Dave asked, how can you tell when resampling will improve the probability estimates?
Excellent question. I would say basically try it. We're all empiricists here as data scientists, and see whether the dot as a classifier is inside or outside your original curve, or is the new ROC curve inside or outside your original. So this gray curve is my original ROC curve. Because this gold one, which was the curve for one of the classifiers, I wish I'd printed the name, because it's inside, it's not improving things, it's making it worse. Now, Dave's point has an implicit point that's very important. There may be situations where it is an improvement, and if you try it and find it, you've done good work. But how you tell, I would say, look at these plots. So a very good point.
Jayanth asks, this may be a bit off topic. Is there a benefit to resampling the rarer class?
Yeah, well, the perceived benefit is the rarer class is not influencing the model as much as it should. And we care about the rare class because the rare class is often something dramatic like dies. So the implied benefit is because it's small and the model doesn't know our intent, it doesn't get treated with the respect it requires. So the principle of resampling was if we make more instances, then the model's forced to treat it as important. However, I personally don't like resampling. Now, somebody else might give a great talk on situations where it works really well. I think most people have had fairly good experiences with resampling, but I think they would have the same experience if they went to a probability model and adjusted the threshold.
Jeffrey asked, it seems as if there are endless packages to choose from. How do you refine your data science toolkit for each new problem?
There are endless packages. There's a Python principle, there should be one right way, but that's not true in the package world. For most clients, I stick to scikit-learn. It's very well curated. I use XGBoost. That's about it. And then I use vtreat, but that's my own baby. So I'm kind of sympathetic to it. A lot of people might use scikit-learn pre-processing one-hot encoder, but I agree with the sympathy. I would pick a small set that you very much trust and only bring them in when they add a lot of value. There is an opposite behavior where people say, I've seen this feature in another language, I'll use this package.
That's all the questions we have right now. So
Cool.
let's just give them another minute or two, see if
We'll
any
give a
more
minute.
come in.
Settle. Yeah, and I'll do the second talk. So this was a polemic talk. And so, I totally sympathize that somebody may have done great work with rebalancing, but they would need to build a graph like one of these to show it doing something. Just because the default prediction at threshold 0.5 looked horrible, that doesn't prove your model wasn't valuable.
Right.
And
I do have one question. Is the Jupyter notebook, is there a link to that included in the GitHub directory we posted? Or
very good question. Yes, the GitHub directory has only 3 items in there, and one of them is exactly this Jupyter notebook.
Okay.
You would have to bring your own data, but it has in the comments where that is elsewhere on GitHub. Yeah, cool. Thank you. I'm going to go ahead and transition to the next talk then. That seemed a good idea, Sean, or a bad idea?
Yes, that's fine. We just have one more question, but let's go forward.
I'm sorry. This is good use of the time.
Are there ways to predict probability distributions for regression?
Yes, that's logistic regression. So it's called a generalized linear model. And I love logistic regression. I happen to use XGBoost here, which is a tree-based method, but I adore logistic regression, and it handles the fact that logistic regression handles the fact that probabilities between 0 and 1. So you'd love your prediction to be in that range in a meaningful way. One could just try regression on probability problems, but then you get negative predictions and 2. As logistic regression, can't recommend it enough. Scikit-learn has wonderful implementations of that.
Okay. We do have more questions, but let's move forward with the next section, and then we'll leave those questions to the end.
I do apologize. I think all the questions have been excellent, and I presume some of the others are excellent. Probably should move forward. And objections are legitimate questions if you have those too. I do understand that was a polemic talk. Okay, so I want to transition using this slide. So again, if we make the mistake of treating classifiers or decision rules as the goal of data science instead of probability models, and by the way, Norm Matloff has been talking in this direction also. He has some excellent work, Professor of UC Davis, Norm Matloff. If we make the mistake of saying the goal of a classification problem is to build a classifier instead of a probability or risk model, we often get to this fallacy. And this, again, I stole from Nina Zumel, who's not here to defend herself. Here are 2 classifiers for the exact same problem. The x-axis of each of these 2x2 grids is the classifier's prediction. The y-axis is the ground truth. And the number in the cell is the count, how many individuals in this set had both those labels of classifier. Correct classifications are where both labels are false. Those are the true negatives. Or where both labels are true. Those are the true positives. Now, this classifier on the left is 99% accurate. There's 1,000 instances, and it said the right answer on 990 of them. This is a completely useless classifier. It achieved that accuracy by saying yes. By saying no all the time. The second classifier is only 91% accurate, but if this was an early medical screening, could save lives. It's only 91% accuracy, but notice it said that 100 people may have the disease. It was wrong 9 times out of 10 when it said that, so it had bad precision, but it has perfect recall. It found all the sick people in a set that is much smaller than the original set, so you could do an expensive follow-up test on these people. So accuracy is not just an irrelevant term, it's often exactly anathema for what you're trying to achieve. You just have to be sympathetic with your business partners. They use the word accuracy because in English, colloquial English, not mathematical, it's a synonym for quality. And when they say, I would like an accurate classifier, they really mean I want a high quality one. Now, again, accuracy is also the technical term for what fraction of the data did you get right, which is what's on this slide, and is rarely your business goal. That's what I want to emphasize. So Nina, the next part of the presentation, which the slides are shared, is what do you do if I kick your legs out from under you and say you can't use accuracy for everything? So this is by Nina Zumel. It was originally scheduled for Baruch Day, but we had some technical difficulties, and I thought I'd removed that from that slide. So anyway, so what do you do? So you have the ROC curve, and if you're a mathematical sadist or brutalist like myself, you just say, well, there's a slope on the ROC curve where the sensitivity specificity exactly matches your business goal, and if you have a master's degree in finance, that's obvious, so you're done. Or if you're a nicer person, you slow it down and build the threshold plot. So this is in R, where Nina very much prefers to work. I work in both, she works in both. And again, she's unrolled the precision recall plot to sensitivity and specificity, and many people can answer the question, what sort of sensitivity and specificity works for you? Or we could ask the machine to do it. And that's what she's pushing here. Or we could do another metric. We could do precision versus recall. Recall is a synonym for sensitivity. Precision, as we see, is different. It's basically when you say something's true, how often are you correct? So basically, accuracy is not often the business goal. What is the business goal? Usually it's utility. And let's define utility. So the first example is sales. You have a pool of 10,000 sales prospect. The base conversion rate's about 1%. You want to know, I'd like to call a couple hundred of these prospects. I don't want to call all 1,000. I would like to call the high likelihood prospects first, because that's how I maximize my effectiveness of my call center. So somebody that has a 2% chance of converting to sale has twice the base rate chance of converting. They're a valuable prospect, even though they're probably not going to convert. So the 2% converters, that's twice the base rate of 1%, I would love to call them. So that's my goal. So let's put in our utilities. Basically, the idea is we can completely classify the behavior of a classifier in a data set by writing down the true positive rate, false positive rate, true negative count, false negative count. Counts are rates, probably counts are better. So if we assigned a value to each and every one of those, that would then say for a given classifier, what's the utility? Now, again, we can sweep out classifiers by using a single probability model and proposing different thresholds. So basically here she's saying, well, a true positive, the value of that is the value of a sale minus the cost of contacting them. A false positive, the value of that is the cost of contacting them. It cost us money to interact with them and we got nothing for it. True negative value is 0, and false negative value is also 0. But hey, let's put a little negative there just to say, hey, I don't like missing things. So that's just maybe their business partner asked for that number. So these 4 numbers define the business policy. And what she's saying is, let's work another example simultaneously. Same data set, we're just changing our interpretation. So this is all fake data. 1% prevalence rate of a disease, but different costs because it's not sales screening, it's screening for a horrible rare disease. So true positive rate value is basically, we have the cost doing the test T, we have the cost of a follow-up test F, and then we have the benefit of early treatment. And I may have screwed up the sign there, I do apologize. It's right in the code. But basically a true positive, we test the person, it says they're at risk. That causes us to do an expensive follow-up test. It also comes out, and then we get a benefit of early treatment. Like maybe we save $100,000 in cancer therapy because we got them much earlier. False positive cost is basically we run both tests. So we have the expense of running both tests, but we don't get that benefit of having actually intervened successfully. True negative cost, we have the cost of running the initial test, but we saved the money on the expensive follow-up test. And then false negative cost, well, we have the false negative value. We ran the test, we ran both tests. Or no, false negative. We run only the first test. We tell the person they're fine. They go home, get much, much sicker over the next few months. And then we have a much more expensive treatment regime for them. So they get a different, much more expensive treatment regime. So the business could estimate either proxies or approximate values for these things. And then software can say, well, the utility of an outcome of this set of false negatives and true negatives, we had 3 true negatives, 2 false negatives, 2 false positives, and 4 true positives. The value of this behavior of the classifier on this data set is then this linear combination of those values the user specified. We can then evaluate that. This is a service supplied by our Sigger R library. That's another wind vector library, this time in R instead of Python. vTreat's available in both languages. It has a function called model utility that you give it your linear utilities, very simple calling, and it builds this graph for you. This says, if you said the people I'm concerned about are at my probability threshold of 3%, they have a 3% chance of making the sale. If you say that's my threshold where I'll put my call staff on them, then that has the maximal expected utility. If you interact with more people, that's setting a lower threshold, you're giving away your profits with the cost of calling people that don't respond. And if you interact with fewer people, you're losing prospects. So it says this is where the trade-off is best. That's the utility there. This graph is a one-liner from Sigger. It's basically sweeping out every possible classification rule given from that probability algorithm and applying that rule and computing the utility, which is just a function of the true positive count, false positive count, true negative count, false negative count, and those 4 linear valuation terms we asked for a business partner for. Then the medical screening is just load up different desiderata, run the same software, and it says for the medical case, the optimal threshold's a little over 1%. That this is where, and it's probably due to the imbalance of how expensive is it to miss, how expensive are false positives? How expensive is it to miss a sick person? It's saying, I'm willing to spend more on useless tests, follow-up tests, because that is worth more to me than missing a few sick people. So it picks exact same data set, just different 4-number desideratas, and we get a completely different threshold curve and a completely different optimal threshold around 0.1, a 1%, threshold around 3%. Notice both of them are very, very far away from 5%. In both cases, the model is saying, don't just go for the people you think are going to say have a 50% chance of doing. Go for people that are probably not going to do it, but try hard. Both the models are saying try hard. This is both situations on the same graph. The medical one is the dotted line decision on the left, and the business one is the dotted decision on the right. Same classifier, same data, just different desiderata. It says, well, for the medical, I like a specificity of, I'll take a specificity of around 0.6 to get a sensitivity of around 0.9. For business, I want a specificity of nearly 0.95, and I will settle for a sensitivity of 0.3. So you don't have to ask any sensitivity specificity questions to your business partner. Just ask them, how do you value a true positive? How do you value a true negative? And obviously there's some symmetries that, it's multiplication and addition don't affect the decision. Yeah, so that's the takeaways. Accuracy metrics are, again, prevalent because it's the standard English term to say accuracy is a synonym for quality. Classification models are basically, yes, to deploy a model, it has to be a classification rule. However, I say delay changing a model to a classification rule as long as possible, because then even your business people could change the threshold on the fly on an already deployed model. So the score is much more valuable than the decision until the very last moment, that when you have to say whether to give a person a test or not. Utilities are great things. Business people are familiar with efficient frontier and utilities, so this is actually in their language, so they're going to be somewhat helpy. And also, if they don't know the utilities, putting some in and making a decision for them and then saying how they hate the decision on practice data is actually gets them, okay, I know I need specificity to be much better than that. I don't like this outcome. So this interactive you can get from this sort of thing is quite useful. Thank you very much for your time. I think actually we're on time and do have plenty of time for questions.
Yes, we have a couple more questions. I think some of them are related to the first part of the talk, but we can go over those. We have one person asking, when data distribution changes, how do you know when to trigger rebuilding the ROC and how to choose the right probability threshold?
Brilliant questions. So the lie in data science is that data distribution doesn't change, and that the test distribution is identical to the training distribution, and that test distribution is exactly like future data, which means not only did we don't have concept drift, we hope we don't have concept drift, but even the prevalence doesn't change. That's actually successfully modeled by the machine learning. And that's why machine learning people use precision and recall, because even though precision encodes the prevalence, which sensitivity and specificity are very careful not to, medical people are very careful. One of the assumptions in data science, which is not stated, is that the data is going to be identically distributed, which medical people are much more careful not to assume. So that's a weakness of all of us. How do you know to redo it? That graphing just says all we need is access to the model and the new data. And you could get a completely different shaped ROC curve and complete the different thresholds. So you'd actually, to answer the specific question, how do we redo it? We'd have to run the prediction on new data and then rebuild the curve, re-optimize. And again, that procedure can be done on test data, so that shouldn't have a fundamental problem. And then again, if it's drifted enough, we would also want to trigger a retraining. But very intelligent point on very neglected topics in data science, that we are usually blind to this because we assume that through our data hygiene procedures, no distributional changes will happen. And we usually don't respect that enough.
The next is a two-part question. How does unsampling differ for low bias models? And the second part is, I noticed you mentioned that within logistic regression, the minority samples are embedded within the mathematics, but what about others that depend on splitting features, such as random forest?
That's a very good point. And I think a good pushback, that a lot of the software like random forest makes specific categorical decisions inside the software, and a severely unbalanced data set can make those decisions wrong. So the interlocutor is correct that unbalanced data sets can break some software. I believe, or hope, are willing to believe that if the random forest software were audited and you say, look, I'm going to do everything inside it in terms of probabilities and be very careful, like I'm going to use deviance as my metric inside instead of accuracy, deviance being the natural metric of logistic regression and a near synonym of cross entropy. I think it's 2 times the cross entropy. So it's basically, I think there are very important models that break on imbalanced data, so rebalancing may be required, but in my mind, I say those are defective models and probably they could be re-engineered to do it. I'm also guessing that the boosting ones may not be as sensitive to class imbalance as random forest, because boosting corrects, well, the original AdaBoost literally reweighted the data by adjusting weights, and the later gradient boostings, they use deviance as the residuals when classifying, so I think they would have some of the merits of logistic regression. I think neural nets probably need the rebalancing. I believe that because they have several layers that I think would cause that to be necessary. So I think I wandered off the question, but I'd like to emphasize that was actually a very good point that I kind of glossed over and lied to you about. So that very good point. Certain algorithms, especially random forest neural nets, probably do need the rebalancing. And I think there was a second part. I apologize.
Yeah, the first part was, how does unsampling differ for low bias models?
So I think there's a slight, probably, we're playing telephone here. The question's been repeated or probably this type. So there's upsampling and downsampling. I don't think there's unsampling, or at least I don't know the term, and I do apologize.
Sorry, it's upsampling.
Upsampling.
My error.
So upsampling, they don't really introduce a deadly bias. Obviously, they bias the prevalence. They do move the prevalence around, but I don't think they introduce any conditional biases past that. So my complaints about them were more about variance. So downsampling increases the variance because it has less data. Upsampling, I don't think it introduces much beyond a prevalence bias, but it makes the rows correlated with each other, which means certain things like significance calculations are now all dead wrong, because the assumption is that every row in your data set was somewhat kind of like an independent experiment. So I get the question, but I would say I'm more concerned about variance control, which is less dangerous than bias, but I'm also concerned about now the rows correlate with each other, and that is also bad. But bias would be even worse. And obviously it does move the prevalence around, which is a bias control, but I think the conditional biases are not as vulnerable. Excellent point.
Okay, we have another question. I'm going to read it very carefully since it's quite detailed. Even the ROC has error rates that we've kind of ignored due to the test data being a sample of the entire population. Sometimes it might be helpful to know how much the error bar is on the predicted utility at the peak. Any thoughts on how to estimate?
It's beyond what we've done, but it's an excellent point. That basically we pretended that the test data set was infinite, that ROC measurement was completely reliable and not a function of the sampling, which is correctly not true. There are, of course, significance models for ROC. I think the wind vector WV plots, you can turn it on and at least ask for that. The utility plot's very simple. It does not have error bars. I would think the math rapidly falls apart and you would need to do bootstrap resampling to estimate the error bars. But it's a really good point. Often I'm in the luxury of very large data, and so that sort of naivete that I did and just not admitting to error bars, one can get away with. But no, excellent point.
He responded, bootstrap makes sense, thanks. We don't have any more questions, so let's give it another.
I have one comment then I'd like to interject. Yeah. When somebody like me is giving a talk on how to improve your procedural hygiene, these other ways to improve it are very relevant. I mean, so somebody saying, I really appreciate somebody saying you're not putting error bars, and that's also because it's basically these last little bits of hygiene only help you if you're doing everything else right. So it's not irrelevant to bring up these things. So I very much appreciate it.
Well, let's give it another 30, 40 seconds and see if we have any more questions. Otherwise, we'll wrap this up.
And I totally missed the live audience. It just, you can look at people, you can see them frown when you're talking too fast, or, I do appreciate this is not the live experience. So all that is available on GitHub. I mean, obviously the URL is a little wonky, but
yeah, we posted the link in the chat if you hadn't, if you're
awesome.
wondering where
Yeah,
those
no, I'm totally
materials were.
blind, but it's basically the GitHub repository, which the link's in the chat. It's github.com when vector examples scoring models. So basically we have all the slides and we have all the Python work. We're not sharing the R work. It just wasn't packaged up like that, but the functions are all available in the Sigger R package. And it's trivial code. I would not be offended if somebody just copy pasted and add error bars and tell me about it, and I'll be very excited.
Somebody just commented in the chat, thank you very much. I'm looking forward to understanding more of this in a year. That must be one of our incoming students.
That's I do a 2-week immersion course, and you will understand this in a year, and you'll not have needed me to tell you. So this use that as a guidance on form your own opinion. That is an excellent way to control your learning. That I'm really impressed by that strategy. None of this makes sense till you see it a second time.
Okay, well, looks like we're out of questions. So thank you, John, for your talk. It was fascinating. I think we got some very good questions and great feedback. And I think you provided our audience with a lot of useful pointers on how to
I wish I could meet them. The expertise and politeness that came through in the questions was impressive. Thank you very much for your respectful time. I really appreciate it.
Okay. And the members of the audience, I want to thank you for your attendance, and I look forward to seeing you in our future seminars. Thank you so much.